The Nicolaus Copernicus Astronomical Center is a leading astronomical institute in Poland. As an institute of the Polish Academy of Sciences, it aims to cover a broad range of subjects in both theoretical and observational astronomy and astrophysics. With almost 200 papers published annually and more than 100 researchers, the Copernicus Center offers opportunities to participate in some of the most important studies in modern astronomy.
Our mission is to do excellent science, studying cosmic objects from close to the Earth to the farthest reaches of the universe. We observe them using both ground and space observatories in the entire electromagnetic spectrum, from radio waves to the most energetic gamma rays, but also beyond the electromagnetic spectrum, like using gravitational waves. We use the existing observatories, but we also try to build our own instruments. And when we try to understand these cosmic sources, we use both simple pen and paper models and the most demanding supercomputer simulations.
The idea of a strong astronomical institute in Poland goes back to the 1950s. In its present form, the Nicolaus Copernicus Astronomical Center was established in 1978 as an institute of theoretical astrophysics equipped with a fast computer rather than a telescope. It became possible thanks to a substantial financial support provided by the United States of America as a way to commemorate the 500th anniversary of Copernicus' birth. Today, the Nicolaus Copernicus Astronomical Center has separate divisions in Warsaw and Toruń, as well as an entirely new department, AstroCent, focused on the detection of gravitational waves and dark matter. The center in Warsaw operates advanced computer clusters for complex numerical simulations, the ground control station for the first Polish scientific satellites, BRIGHT, as well as a small telescope for training PhD students. Astronomers from the Copernicus Center are involved in a number of major international projects and participate in many of the most groundbreaking astronomical discoveries. Historically, the Institute has made vital contributions to the understanding of accretion processes around objects such as black holes, white dwarfs, and neutron stars.
A pioneering work on this subject was made by Professor Paczyński, who started very advanced studies on evolution of binaries with common envelope and accretion disk, and also he made first steps in computing accretion disk structure. Now, about 1/3 of people working here work in this topic. On one side, scientists here do very hard theoretical work trying to solve what processes are responsible for the emission in those sources. On the other side, they are involved in building modern observatories whose goal is to observe accreting objects.
High-energy processes in the universe can also be observed from Earth's surface. The Copernicus Center is involved in the development of state-of-the-art instruments designed to detect such phenomena.
SAMP is currently the national coordinator of the Polish involvement in a high-energy stereoscopic system, which is the very high-energy gamma-ray observatory in Namibia. It uses very large optical telescope to observe gamma-ray showers in the atmosphere. This involvement allowed not only us, but many scientists in Poland to get involved into CTA. CTA is a Cherenkov telescope array. In the future, it will be really the observatory for gamma rays.
The main source of information about the universe is still visible light, observed primarily with ground-based telescopes. The Copernicus Center uses some of the most advanced optical instruments in the world.
Ground-based observational astronomy at visual wavelengths is very strong in our institute. Not only do we have access to the state-of-the-art instruments and telescopes of the European Southern Observatory, but we also regularly use such big mirrors as SOLT telescope in South Africa. The center also builds its own observing infrastructure. For instance, we have Project Solaris, which is a grid of several telescopes scattered across 3 continents, and the newest addition to our observing base will be several telescopes with diameters of up to 2.5 meters, which we are going to build on Cerro Armazones in Chile, just next door to the extremely large telescope.
The light coming from the stars reveals that some of them change over time. Such variable stars are another important part of research at the Nicolaus Copernicus Astronomical Center.
There are some stars that we can learn more from than from other stars, namely stars that pulsate. Pulsating stars, they reveal something about the interior structure. We use those pulsations as seismic waves. That way we can determine how they spin in their interiors, how large are their cores, how large the stars themselves are, how distant they are. To get the data that we needed for these observations, we need very high precision measurements, so we use ground-based telescopes. We use space satellites, spacecraft like NASA missions, Kepler and TESS, but also our very own bright constellation.
Among all the stars in the universe, the most exotic objects must be neutron stars. These supernovae remains turn out to be perfect laboratories for fundamental physics.
What these objects are incredibly compact stars in which you have a mass that's approximately that of our Sun, but compressed into a 10-kilometer radius, basically the size of a city. And the densities inside are higher than the densities of atomic nuclei. And here at the Copernicus Center, we study all aspects of neutron stars. So we study both the microphysics, so the theory of how matter should behave at these densities, but we also try to understand how to use standard electromagnetic but also gravitational wave observations to put constraints on our models and really understand what the fundamental interactions are doing in this regime.
Stars can also be very interesting when found in groups. Stellar clusters are important sources of knowledge about the evolution of entire galaxies. Scientists from the Copernicus Center have developed a unique tool to simulate such cosmic aggregates.
For over 25 years, we have been developing a modern and efficient Monte Carlo code called MOCA that is used to track in the smallest details the dynamical evolution of star cluster and the movement and evolution of any type of individual objects in the cluster. The MOCA code was successfully used in many international projects connected with different types of black holes and their mergers, tidal disruption events, evolution of population of different types of binaries, and many, many more. The MOCA code is one of the fastest, most developed and efficient codes able to follow the complex dynamical evolution of star clusters.
One of the most groundbreaking achievements of modern astronomy was the discovery of gravitational waves. Scientists from the Nicolaus Copernicus Astronomical Center are active participants in the LIGO-Virgo collaboration, responsible for finding these ripples in space-time.
It's a completely new way of studying astrophysics because we really see things that we didn't see before. We can study populations, test general relativity, whether Einstein was right or wrong, and discover things that we didn't even know exist. So this is really exciting. And on top of the theoretical aspects of astrophysics that we are interested in Copernicus Center, we are very much also interested in the developing new methods of data analysis. So we are using machine learning, and we also contribute to maintenance and improvements of detectors. We are working also in this direction at the Copernicus Center.
With the detection of gravitational waves, possibly the biggest unsolved mystery of the universe is dark matter. Scientists from AstroCent are working on cutting-edge technology aimed at detecting such phenomena.
By detecting the gravitational waves and searching for dark matter, we are exploring the hidden universe. We built a large detector underground and use this detector waiting for the signal from dark matter. To do that, we need to develop really the sensitive device. By using the cutting-edge technology, we also try to contribute not only science, but also medical and industrial applications.
The Nicolaus Copernicus Astronomical Center continues its historical legacy to provide a place for international cooperation on the most advanced subjects in astronomy and astrophysics. From theoretical concepts to groundbreaking observations, scientists working at the center keep pushing the boundaries of our knowledge of the universe.